Good afternoon, everyone. Welcome to the UFS webinar. This webinar is hosted by the NWS OSTI. The goal of this webinar series is to enhance communication and share advancements in all aspects of the UFS, in both research and operational settings. Okay, so I'm Stacy McKell, and I'm here to help coordinate and deliver the webinar. Feel free to contact us at OSTI if you have any comments or suggestions. Here are a couple of housekeeping slides that I would like to show and I would like to bring to your attention. Okay. Due to the high number of attendees, you will be in listen-only mode during the event. You will not be able to unmute. If you have any questions now or during the event, please submit them via the Google document that will be provided in the chat box. Presentations last for about 45 minutes, followed by Q&A for 15 minutes. Type your questions in the Google document during the presentation. All right, today's webinar is going to be the Common Community Physics page, also known as CCPP, and its role as an enabler of hierarchical system development. Excuse me, I always get tongue-tied with that word. So before we get started, I wanted to just quickly let you know how to sign up for the webinar notifications. What you would do is go to the ufscommunity.org page, which I will show you now. Okay. You scroll down to the event section, and that event is here, UFS webinar series, and it will show you today's event. If you want to see past events, you go to UFS. Oh, for some reason I have a privacy error. Well, anyway, you will go to the UFS webinar series, and it'll show you all of the archived events. And this event and all webinars they will be recorded and made available on this portal. So feel free to go through this portal and view all of the past events, including this one. Today's speaker, Ligia, Bernardet, and Mike Eck, will be introduced by Louisa Nance. Louisa, you feel free to take it away.
All right, thanks. Welcome, everyone. It's my pleasure to introduce the speakers on today's webinar on the Common Community Physics Package, or CCPP, and its role in hierarchical system development. Dr. Ligia Bernardet started her career in Brazil before coming to the US, where she received her PhD from the Colorado State University. Ligia is currently the Deputy Chief of GSL's Earth Prediction Advancement Division. Ligia is passionate about creating mechanisms to facilitate synergistic interactions between the research and operational NWP communities. For this reason, she works on developmental testbed projects that engage the academic community in the development of NOAA models. Over the last 5 years, Ligia has been the NOAA co-lead for the development and support of the Common Community Physics Package, or CCPP. On a more personal note, it has been my pleasure to work with Ligia since the DTC's founding back in 2003. Dr. Michael Eck joined NCAR in 2018 as the director of the Joint Numerical Testbed. Before NCAR, Mike was deputy director and the land team lead at NCEP's Environmental Modeling Center. Previously, he worked at the Oregon State University on land and boundary layer model development. Mike is a former AMS Hydrology Committee chair and is involved in a number of national and international activities in Earth system model development. He received his PhD from Wageningen University in the Netherlands in 2005. And I also have known Mike since the early days of the DTC, when we discovered we were both Oregon State alums. So with that, I will turn things over to Mike and Ligia and let them start presenting.
Okay, can you hear me?
Yes, we can hear you.
Fantastic. Well, some technical issues have come up, so Stacy's going to drive for us. So I wanted to thank everyone, or thank you for the invitation for us to present the Common Community Physics Package and its role as an enabler of hierarchical system development. Louisa, Wageningen is always hard to pronounce, so there's the pronunciation. So we have a large development team and also some other people from DTC that are very helpful in what we're providing. So let's go to the next slide.
Stacy, can I ask you a favor, please? You seem to be presenting from the Google Slides. That will cause a problem with the formatting of many slides. Would you be able to download that link and present it from PowerPoint?
Okay, I will do that now.
Thank you so much. Sorry, Mike.
No problem.
Downloading now. Okay. Okay, here we go.
Yeah, apologies to everyone. I seem to be looking over you. It's just how my laptop is set up, because I don't have a camera connected to my big screen, so I have to refer to my open laptop. There. Oh, almost.
Almost. We will editing and present. I'm trying to get into presentation mode.
Along the bottom bar, if you go toward the right, yeah, there you go. I think I see your cursor right there.
Okay, no. Down.
So, very bottom of the screen, and where it's grayed out now, if you go 1, 2, 3 over from the left. Keep going. I mean, sorry. Yeah, 3 from the left, but on the right. So one more that says slide sorter. Keep going,
Okay,
right there.
right.
Show slide.
Okay.
Fantastic. So research to operations. There's a lot of information out there that we need to rely on. And if you tab or click or advance just one. So hit the tab bar.
I did. A tab.
Okay. And once forward. Okay, once again. Okay, so the previous paradigm, tab. There's a lot of great research out there, and I just happen to name several journals that have a lot of really good research in it. So tab, the question is, a lot of that needs to be identified and transitioned somehow. A previous paradigm, tab, might have been to kind of toss it over the fence. Well, certainly we've gotten an awful lot better with that. DTC has been very helpful in trying to move this along, tab. But how can we help to improve this process, improving research to operations? So tab for the next page. What is it? What is hierarchical system development, tab? Well, just from taxonomy, it's an arrangement or classification of things according to the relative importance or inclusiveness and so on, tab. In Earth system model development, we call it hierarchical system development. Basically, it's a systematic approach where we test small parts like physics schemes of an Earth system model, first in isolation, then we progressively connect all those elements with increased coupling between the Earth system components, land, atmosphere, ocean, sea ice, and everything, and all the atmospheric physics, all the way up to a fully coupled global model, tab. System here refers to really an end-to-end process where you include the data ingestion, the quality control, data assimilation, modeling, post-process, and verification. So the whole package. So tab. So it's really necessary to have some efficient infrastructure to connect these steps so you can have an effective R to O to R process. Next, sorry, tab. So why do we need it? Tab. Well, to really understand model biases, we often need to simplify the atmosphere as one of those Earth system components down to a few key processes and interaction, tab. Because we also can save compute resources by identifying and fixing bugs maybe earlier on in the testing process rather than running the whole model, tab. And there are many Earth system processes to consider from local to regional scales, tab. And here's an example of a lot of interactions that are going on. And this isn't just conceptual, this is actually taking apart all the physics for the land, for the boundary layer, and for the radiation in a simplified mode to just look at those local interactions. But that goes all the way to the regional, tab. So all of those local interactions are on all parts of that schematic with similar ones over the local ocean atmosphere interaction or ice and snow and all that, tab. So some background. If you tab again, there was a climate workshop in 2016 where the climate community talks about a hierarchical approach to test their Earth system components. And you want to test them individually to better understand what's going on because it does save on those CPU resources. And if you're running climate simulations, you can't very well run a whole test for a decade to really see how something's behaving. So it's better to do that in pieces. So before you expend all those HPC resources in a fully coupled simulation. And what I like is the quote from tab, the next from one of the model participants, Tim Palmer from University of Oxford, the Met Office and European Center. He said, hierarchical thinking should be second nature from all of us weather and climate scientists. And here's on the right is just the link to the workshop. And that's kind of where I first started thinking about this and borrowing this, thinking that this definitely does work for NWP. If you go to the next tab, or if you tab, Julius Slingo, who used to be the chief scientist for the Met Office, did a very nice 2017 review of WCRP. And basically, the findings came out, a couple of the important ones, talking to her, increase the focus on process level understanding for model improvements. It's just not the final metrics, but it's looking at everything under the hood and connect weather and climate somehow. Tab. Also, Kristen Jakob, who is very much involved in the World Climate Research Program from Australia, he did a very nice article in 2010 in BAMS, basically to address long-standing systematic errors. The community needs to improve the diagnosis of key processes contributing to these errors, and more model developers are needed. And in talking with him, he said, geez, I wrote that in 2010, and we're really trying to work on making progress in improving those key processes. Tab. If you go to the, one more tab, ufscommunity.org website, there's a nice article that I put together that leverages some of his work here, tab. And there's a little cartoon that just shows I won't go through it, but it shows the fact that it's a multi-step process and there's a number of loops to work on to get get after making the improvements so that they're very robust and not just maybe tuning, but actually have a robust effect. If you go to the next tab. So let's look at this from from simple to more complex, comprehensive approach. So go ahead and hit tab, 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 and one more tab. So if you look at single processes, just the surface layer and the surface layer drag, surface layer fluxes, whatever, that's a part of a model, but you can go all the way to the complex system, the global coupled model. So in terms of the understanding, you can certainly understand a lot when you just focus on a single process. You can understand a lot about that process. But as you go to the fully complex system, you can't understand as much about the single process as you can about the whole system. So there's a hierarchy of looking at different parts of this continuum from single processes to fully complex systems, and there's some understanding you can gain and then hopefully improvements you can make. So tab, and go ahead and just tab, keep going, 1, 2, 3, 4. Since I can't do this myself, it's probably easier to just show it. Keep going, tab, tab, tab. Great. Okay. This harness basically is essentially looking at a single process simulator, but the next step would be a single column model. The little arrow going back just suggests that your single column model can be subdivided into pieces, just simulating one single process, just like that single process over on the far left. 2D models, we really haven't gotten there, but that is a step as well. Limited area models, regional models, global models, and then fully coupled models. Limited area model might be just so that you can focus on a 100 by 100 kilometer box to focus on convection. You don't need to run the whole model. You don't need to run it across the globe for a long period. You just want to start exploring this. The single column model, of course, is something that you can look at the physics interactions just in a single column. Tab then. You need to make process level assessments throughout this harness. And so that would be, am I getting the right surface flux? Am I getting the right surface drag? You need to make sure that you're getting that when you're just looking at that single process. But when you go all the way down to the fully coupled model, are you still getting the processes right? So there's process level metrics that can be examined throughout this this hierarchy in this testing harness. Tab. Now, what you need to do for each of these steps is somehow drive and validate the model using observational data, model output. You can use that to drive the model, or some idealized data sets, basically just to explore the behavior of the model physics. And I say cumulative benchmarks because you want to get the process level right at one step, and the next step, and the next step, and the next step. So, you know, it's a lot of cumulative benchmarks that you need to get right. Go to the next tab. Oh, that's just to show processes again, a lot of processes. And finally, the next tab. The simplest framework is shown with that little triangle or diamond, and the single column model, and then the associated physics process simulator allows you to look at that inter-suite connections, or I'm sorry, the inter-suite physics interactions, or just the simple simulator, because if you take a single column model and you have on-off switches for the physics, you can address that. And that other, well, that should be a star, and it says may involve cold starts or cycled runs, should be a star, so that could include data simulation as well. So we're covering the gamut of things. Tab, next slide. So these are just examples. We'll go through these kind of quickly. It's essentially hit the tab once again, and once again. The upper left is where we're just focusing on just one subcomponent of the surface moisture flux. On the upper right, you're looking at just one piece of the surface heat flux, a subcomponent. And basically, we learn some things based on this focus on the process. Similarly, on the bottom left is just looking at the land model and trying to look at systematic biases using data sets that allow you to see, well, how is it behaving throughout the year? How is it behaving diurnally, different seasons? And then finally, the single column model, we learned a lot of things about the land atmosphere interaction. But the thing is, tab, one more tab. These are all one-offs, really one-off studies. So go to the next tab. So how do we use this? How do we make it work? So tab. How do we make this hierarchical system development work for R2O? And go to the next tab. And one piece of this is the Common Community Physics package, tab, where the CCPP is an important enabler of this hierarchical system development process. So we'll switch over to Ligia.
Okay.
Next tab.
Hi, everybody. Good afternoon. Thank you, Mike. Thank you, Louisa, to start with. Thank you, Stacy and Mike, for getting us started. I think we are running like 10 minutes behind on where we wanted to be, Mike, with our slides. So I'll try to catch us up a little bit and leave you to catch us further up for later on in this talk.
Yep.
So as Mike mentioned, this hierarchical system development is very important, and it is something that the CCPP can enable, and that's what we want to talk to you about. So the CCPP has three elements. The first one is the CCPP Physics, which is a library of physical parameterizations, the Ccpp Framework, which is the software infrastructure that allows using the CCPP physics in a host model, and finally the CCPP Single Column Model, which is a simple host that employs the CCPP physics and framework. All of those are developed openly, and we have listed here the GitHub repositories where those developments can be found. Next slide. This slide shows the CCPP architecture. At the bottom of the slide, you see a gray box, and that's the CCPP physics. That is the collective of physical parameterizations where we have several of each type. So several surface layer, several boundary layer, convection, etc. And when the CCPP is used in the developmental research settings, we also have some chemical schemes inside the CCPP physics. So the physics connects to the host model via the CCPP framework. And the host model represented here is this atmospheric driver, or this yellow box at the top of the model, the top of the diagram. And the atmospheric driver calls not only the physics, but also the dynamical core and other processes in the model execution, such as coupling. So the connection between the physics and the host is done through the CCPP framework, which is represented by these purple boxes on the right side. And more in particular, we use metadata about the variables that are requested by the physics and provided by the host model to do the exchange of information between the physics and the host model. So the CCPP framework uses this metadata to auto-generate physics caps before the model is built. And then these caps, along with the rest of the physics and the host model code, is compiled together to create the model executable. And then at runtime, the framework is used to pass the variables between the host and the physics. And the last thing to point out here is that the physics can be called in bulk. Like we have here this physics cap pointing to the big gray box at the bottom, but physics can also be called from more individually. And we have the example here of a physics cap connected to the die core. And if you're familiar with the way that GFDL microphysics is used in the UFS, you know that fast microphysics processes such as condensation are called directly from the die core. So we can enable that. And so all this relates to hierarchical system development because we can use the CCPP with a variety of host models. They can be three-dimensional models, UFS and others, as well as simplified models. Next slide, please. So we're going to move on to CCPP physics. Next slide. This shows the various parameterizations that are available in the CCPP physics. So the first column shows the types of parameterizations, microphysics, planetary boundary layer, surface layer, etc. And the second column shows the schemes that are available in each of those categories. So for example, for microphysics on the first line, you see Zhao-Carr, GFDL microphysics, Morrison-Gettleman 2 and 3, Thompson, and Feria-Legal. So similarly, for each type, there are a variety of schemes that are today part of the CCPP. And the color coding represents the implementation, and you see that there are several organizations, groups, and individuals contributing physics to the CCPP. So it's a true community effort. Next slide, please. And you can hit the tab. So in terms of new contributions coming to the CCPP, we have a few new schemes coming to the horizon, on the horizon. So the community land model, CLM, lake model is being added by the NOAA Global Systems Laboratory, and NOAA Severe Storms Laboratory is adding their two-moment microphysics. There's also an effort going at GSL to make some of the schemes GPU compliant. And finally, EMC is working on the transition of the NOAA MP land surface model to refer to its authoritative repository. So in terms of source code, for certain schemes, the vast majority of the schemes with the source code is directly in the CCPP physics. And for a minority of the schemes, we refer using a submodule to an external authoritative code repository. You can hit the tab, tab. Yeah, tab, and one more tab. Going forward, we see lots of opportunity for streamlining and modernizing the existing code, and we hope to invest resources in that vein to make the code more and more friendly as we go forward. Next slide, please. So the slide is to provide you with a little bit of information about what makes a parameterization CCPP compliant. Tab. So the first thing is that the parameterization is contained in a Fortran module. Tab. And then one of the 5 possible phases of a scheme, such as init, run, finalize, etc., needs to be contained inside this module. So in this example highlighted here, we have a scheme called my scheme, and the phase depicted here is the run phase. Tab. Every scheme in the CCPP must be accompanied by metadata, including information about its dependencies. So that is so that at compile time, the framework can know what all the Fortran files that are needed to compose a scheme. Tab. Finally, each CCPP entry point subroutine must be accompanied by metadata about all the variables that are passed in and out of the subroutines. Tab. So in this example here for variable NI, we see a description of its standard name, long name, units, dimensions, type, intent, and whether it is optional or not. Next slide. As I mentioned, there are 5 possible phases of a CCPP scheme. The init and finalize phases are invoked just once per model run to initialize the physics, for example, read and broadcast, look up tables, and clean up allocated memory. Tab. And the other 3 phases, time step init, run, and finalize, are time dependent that are executed once each time step. Run executes the bulk of the parameterization during integration, and time step init and finalize take care of time dependent but operations that are independent of the domain decomposition. So next slide. A few more things about CCPP compliant schemes. Schemes cannot stop the model, but must gracefully pass stop error flags and error messages to the host model. Schemes should be written modern Fortran, so not have common blocks, explicitly declare all variables, and avoid go-to statements. In order to enable compiler bounds checks, schemes should use assume shape array dimensions. And finally, all schemes have hooks to scientific documentation. Tab. The schemes should have markup comments that are used by the Doxygen software, which are then enable the creation of the scientific documentation. So this example just shows some of these Doxygen markups that are right above the subroutine my scheme run and are a trigger for insertion of Doxygen content here. Next slide. So as I mentioned, this metadata, every scheme has metadata about the variables that are passed in and out. This metadata is parsed by the CCPP framework and the Doxygen software to create scientific documentation such as the one shown here. So this particular example is for CCPP version 5 and is part of the documentation of the GFDL cloud microphysics. And we see the argument table where all that metadata about the variables in the subroutine is described, their names, their units, kind, etc. Next slide. The scientific documentation also is not restricted to parsing inline comments that are in the Fortran code, but can also include text files, images, equations, etc., and all that gets parsed and displayed in a HTML. And the link is there at the bottom. Next slide, please. So a big effort we have been engaged with recently is the creation of a dictionary and a set of rules for the CCPP standard names. So you already heard the word standard names a few times today, and they are a key aspect of the CCPP as they are used to communicate variables between the host model and the physics. So whenever possible, we use CF convention. We draw from the CF convention when creating standard names for the CCPP. And when we cannot find a name for a certain quantity, a certain variable in the CF convention, we have to resort to invent a name. Tab. This has been working fairly well because, hey, we have a working CCPP today. However, the lack of rules for the creation of new names has led to a proliferation of names without much law and order in terms of how they are composed. And also we lack a mechanism to share existing standard names among the many developers that may need to know what those standard names are when they bring a new scheme into CCPP. So recently, Tab, we have created a new code repository which houses the rules for creating standard names as well as a dictionary of the names that are currently in use. Next slide. This is the last slide about the CCPP physics, and it pertains to another big effort we're engaged at right now, which is CCPP physics code management. This has been a multi-institutional effort involving DTC, the Navy Research Laboratory, NOAA, and NCAR. In terms of defining how we want this collaborative effort to look like, how do we want the community of scientists and students and everybody in the community to view the CCPP, how are they going to come get the code, come get information from all of us that are developing CCPP physics. And we have addressed a number of topics so far. Some examples are listed there: the structure of code repository, the standardization of the names of the schemes, responsibilities for reviews of pull requests, best practices for interoperability, and the standard names I mentioned in the previous slide. Next slide. So this brings me to the end of the CCPP physics, and now I have a few slides about the CCPP framework. Next slide. So one important aspect of the framework is how the CCPP physics is used. So the physics is a collection of individual schemes, but the way physics is used in a host model is through suites. Suites can have one or more, typically more, schemes. And the CCPP framework uses a suite definition file, which is a file in XML format, to describe which schemes should be called by the model at runtime. So this suite definition file enables various aspects of the hierarchical system development. So one thing is that it is very easy to change the order of the schemes because the suite definition file is basically an ASCII file that lists which schemes are going to be called in which order. So of course this needs to be done with caution because variables need to be ready to be ingested by a scheme. So when changing the order, be careful. But we do have this ability to assemble these small blocks, which are the schemes, in different ways, and that's why we call this hierarchical system development. The framework also allows grouping, so you can call certain physics, go do something else in your model, and then call more of the physics. And we also enable subcycling and iterations in which some physics schemes can be called at higher frequency than others and higher frequency than the dynamics. Next slide, please. The CCPP framework needs to pay attention to a couple of very important things, which are performance and flexibility. So for operations, for using operations, the CCPP must run fast and have a low memory footprint. However, for research, it's important that the framework provide flexibility since researchers want to run the model with, in a variety of different ways. So a few of the capabilities we have to support that. So the first bullet there, when using the CCPP, a physics driver is not employed, and that makes the model run faster. So a physics driver in a traditional model is that piece of Fortran code that will say, well, if I chose microphysics number 8, call Thompson, but if else, go do something else, and else, go do more different things. So by avoiding all these if-else statements, we can have faster execution. The second bullet talks about our multi-suite build, which again enables performance and flexibility. So at compile time, a user can specify various suite definition files, so various suites, and then all those are used to create a single executable, and then at runtime, the user can choose which suite they want to use. So this brings that flexibility of using multiple suites with a single executable. And then a third thing in terms of flexibility is this automatic unit conversion. So tab. In this example here, we're talking about a variable which is effective radii of ice. And we have a difference between how the host model and the scheme, in this case, the ThompThumb microphysics, we have a difference in the units of this variable between the host and the physics. One is in micrometers on the left side, and the other one is in meters on the Thompson microphysics on the right side. So traditionally, a developer would have to go in and write a subroutine or a little interstitial code to do this type of unit conversions. But the CCPP framework is able to identify that those two variables are the same because they have the same standard name and do the conversions on the fly. Next slide, please. We're looking at a number of improvements for the CCPP framework, improvements and additions, and those are listed here in this slide. Some are already funded and in progress, some are pending, some are for the future. So we're working on a few things to facilitate addition of new schemes, that is automatic array transformations. So when the host and the physics have different array layouts, we want to automatically be able to transform those. Calculation of derived variables. So when the host and the physics have different variables, but one can be derived from the other, the framework can do that automatically. And the vertical flipping of arrays to more easily use parameterizations that are ordered bottom to top or top to bottom. Tab. We're also working on improving debugging and investigation of the schemes by improving how we do error handling, by extending diagnostics, and also we're working on a visualization tool for how variables travel through a suite, which will be able to give us information about, given a certain variable, what are the schemes that ingest it and even modify it. Next, sorry, tab. That was the graphical tool there. So next slide, please. A few more things we're working on is enable new capabilities in coupling. So we have future work planned to make so the schemes can either update the model state or return tendencies so that the suite definition file can choose to run a suite in either process split or time split integration. And finally, we plan to generate mediator caps, so like NOAA mediator caps for CCPP schemes so that certain components such as a land surface model can more easily be run as a component through a coupled system or as a CCPP scheme. Tab. We're working on increased performance with the ability to run single versus double precision physics, as well as having the capability to dispatch physics to GPUs or CPUs. Tab. And finally, we have a goal to create greater independence from the host models by saving states for physics restarts, improving handling of constituent arrays, and abstraction of surface composites. And in interest of time, I'll skip this figure here. So that brings us to the next slide, which is the third element of the CCPP, and I will hand the baton back to Mike.
Okay, thank you very much, Ligia. Can you hear me?
I can, yes.
Okay, great. Go ahead and tab. So we talked about the single column model in the context of the whole hierarchical system development. If you would tab. So what you need to do for the single column model is provide an initial state of the temperature, moisture, winds, and that can be from observations, some idealization of the atmosphere, or you can take model output. Forcing is applied, and what that does is it mimics that column state as if it were part of a three-dimensional model. So it replaces the die-core, and then the physics responds to changes in the column state, and in turn changes the column state. And the end state is simply a combination of the forcing and the physics. So if you tab again, certainly the pros for this are it's very simple to develop, it's easier to interpret, and it's very computationally inexpensive. I can make a lot of simulations and learn a lot about my physics interactions. Tab. Of course, it is sensitive to the forcings, and it's a necessary but not sufficient condition to actually make improvements to the model. So tab. This rather busy slide is basically those first steps that I talked about providing the initial state and then the forcing in some manner that replaces the die-core comes in. That's where that FE3 is. You can get, again, from field campaigns or other data sets. You essentially get a data input file, and then there's a number of things that you have to, configuration name lists about the physics that you're using. Ultimately, then you end up running this model with this with this forcing data to replace the dynamics, and essentially then you get an output at every time step of those fields. Tab. Tab again. So there's a number of cases that we have right now. Some are maritime, some are continental that we're developing. Tab. That are part of the available cases that we can use. And our goal is to generate many single column models cases for the model physics development community and leveraging a number of measurement networks and field campaigns, including the international community, where we've adopted the International Single Column Model DEFI format, which really opens the door for a lot more cases. Tab. And these are just simply a little schematic that says there's a lot of cases out there, and we're just trying to leverage all those. Tab. Just some examples I'll go through real quickly. Basically, we're using the single column model to study the sensitivity of the model results to the heat flux. And these happen to be a potential temperature profile throughout various times of the day, looking at controls versus tests. We want to find out what the sensitivity of the model is to certain changes we do. Easy enough to do a control versus what we change. And it's very easy to then isolate those processes. Next, tab. This is another one that just reveals the PBL is sensitive to the surface heat flux. The boundary layer depth definitely responds to the surface heat fluxes. And so this is just looking at that case for test versus control. So many, many more possibilities exist. Next. Go ahead and tab again, and tab again, and once more. Essentially, the Model Uncertainty Model Intercomparison Project, MUMIP, is an international effort to try to better understand the model physics uncertainties and how that can be represented in stochastic physical parameterizations. In this case, we'll run approximately 40,000 single column model simulations. Now, what this is coarse grain data. So we use a very high resolution model, and then we map to a coarse grain nominally in the bottom left that it says that the GEFS resolution. So basically, then we take high resolution output from a high resolution model, and then we coarse grain it, and then we run our single column model, and then compare that with then what was from the high resolution model. And that can give you some understanding about the scale dependencies and the model model uncertainties in the physics. So this is very nice. We had just started working with this, and there's a number of participants, Oxford University, UK Met Office, us, European Center, and others. Tab. Just the SCM Outlook, a tab again, and once more. Go ahead, and once more. We're adding additional cases. Oh, sorry, back one. Go back one. There we go. We're just adding more additional cases. We'll keep doing that. This is just another subset of those most recent ones. Column replay mode essentially says we take output from the UFS, put it in the single column model, and that gives you a benchmark for what the answer is in just the single column mode, and that allows you to isolate the physics a lot more easily. And then something that I talked about as well, that little arrow going from single column model back to process, arbitrary physics subsets. We basically put on-off switches for the physics in the atmosphere, for example, and then allows us to further isolate processes in the atmosphere, surface layer, PBL, microphysics, radiation, etc. Tab. Which takes us to the next piece, which is CCPP dissemination. So I'll let Ligia take back over.
Okay, thank you, Mike. So we've had 5 CCPP releases, public releases up until now. The second column there shows the date. So we started back in 2018 and our last release was in March of 2021. In each release, we'll typically have one set of operational physics plus several developmental schemes and suites. That's because we want to support research and also support the development toward upcoming operational implementations. And as far as the host models, each of these public releases have been are tested and supported for use with a given model. Always the single column model, but then also the UFS weather model and or the UFS medium range weather application or short range weather application. Next slide. This shows our supported suites. So on the top line, you see again that we have operational suites as far as developmental suites. The second line in blue shows the suite name. So a couple of suites on the left side are from the GFS v15.2 and GFS version 16. Going toward the right, there are more developmental suites. On the very right, we show the RRFS version 1 alpha. RRFS is the UFS rapid refresh forecast system, the 3-kilometer regional configuration, which is being tested for future implementation. And then the third line says shows the host there in green. Again, suites are not always supported for use with every single host. So depending on the suite, they are more applicable to a certain host or another. And then the rest of the table just showed the types of schemes and which schemes are used in each suite. And in bold color, we see schemes that differ from the first column, from the GFS v15.2, just to give you an idea that there is a fair amount of diversity of schemes among all these suites. Next slide. Here we have information about users and how users and developers can get a hold of the code and get a hold of our support and also general community support. To use the CCPP. So the first link there is our main hub for where people can get the code and support. We have a CCPP forum hosted by the DTC where anything about CCPP and single column model can be discussed. There is the UFS forum. We have scientific technical documentation, a user's guide about using CCPP with the single column model. We host GitHub discussions where developers can talk with us and with one another about CCPP development. And we have several tutorials available, online tutorials, which include both video presentations and hands-on exercises. The next slide. We have several capabilities enabled that support development for the UFS. So since this is the UFS webinar, it's appropriate to bring this up. So in terms of GFS version 17, we have a baseline for that. As you may know, the currently operational GFS 16 does not use CCPP, but we created a CCPP compliant emulation of it to serve as a baseline for the GFS 17 development. For GAFS version 13, which is the upcoming implementation, we have several GitHub branches established for collecting physics and developments for the prototypes for the GEFS, the Global Ensemble Forecast System. And then for RRFS, which is the Rapid Refresh Forecast System, and HAFS, which is the Hurricane application of the UFS, we also have all schemes needed for initial testing and development of those applications. Next slide. In terms of CCPP transition to UFS operations, here's a table that was adapted from some slides by Vijay Talapragada and co-authors. So we see on the left side of the table, UFS implementations that happened up until 2021 that did not use CCPP, and those are for the GFS and the GAFS. And then going forward next year, 2022, there will not be any operational implementation due to a moratorium for changing the operational computer. But then starting in 2023, we'll have new UFS implementations, operational implementations, which will use CCPP, starting in 23 with HAFS and RRFS, and then in 24, we should have CCPP being implemented in the GFS, the GAFS, and then the version 2 of HAFS and RRFS. Of course, this is all subject to change, but that is the current thinking. And finally, I'd like to highlight that this has been a highly collaborative effort. So we definitely want to thank everybody in the community, from NOAA, research laboratories, the Weather Service, NCAR, universities, the Navy, and everybody that has been contributing to the CCPP. CCPP is being used now in experimental versions of the Neptune model that has been set up by the Navy Research Laboratory, NRL. And additionally, the CCPP framework is being adopted and enhanced for using NCAR models. So NCAR is doing a lot of development of the CCPP framework. And this happens under the umbrella of the NOAA NCAR Memorandum of Agreement that was signed back in 2019, which set the intention for NOAA and NCAR to collaborate in the infrastructure for model development. So with that, oh, I'm sorry, I forgot to say next slide. Stacy, please go to the collaboration. So this is where I was talking about the collaboration both with NRL and NCAR under the NOAA NCAR Memorandum of Agreement. So please now go to the next slide, and that's the summary. And Mike, I think you're going to go over this one.
That's fine. Just go ahead. First tab. Earth system models for weather and climate becoming increasingly complex. So we have to think how we can best do that. And we're trying to get after the right answers for the right reasons. Tab. So the hierarchical system development approach, as explained earlier, is a very good way to look at small elements first and then progressively connect them so that we can see, are we getting the right answers for the right reasons, all the way up to fully coupled models. Tab. The common community physics package is that efficient infrastructure and set of physics to then connect these steps. So essentially to examine that model physics. And so it makes that R2O to R process for physics improvements more effective. Tab. So the CCPP is under active development with new parameterizations, framework capabilities are being added, institutional governance. So it's not just kind of a one-off. This is something that's very well organized and in use by the community. And this is one of our primary efforts for a solid foundation for the CCPP use by researchers and by research and operations as well. So next, one more tab, and this is the link on DTC for CCPP. And thank you for everyone's attention, and I guess we can entertain some questions.
Okay, thank you so much, Mike. Thank you, Ligia. If you look on the right side of your of the panel, you can pull up the Google document with the questions. Can you see that, Mike? It's in the chat. If you go down to the chat, or you, Ligia, it's in the chat.
I can see it. Yeah, I can see it.
So you can click on the link, and you'll be able to access the Google document where you see the questions.
So I think the first question is
Okay.
from Mike B, which might be Mike Barlage. He says, I don't know if I missed this, but is there a plan for a collection point for community contributed SCM cases? For example, columns extracted from simulations where there are known issues. Hopefully cases that also include observations, maybe flux tower locations or sounding sites. Mike X, do you want to take that one?
I can answer that simply, absolutely. And that's what we were trying to allude to. And I think the international DEFI format allows us to engage and interact with a number of researchers globally that are working on such things and putting some data together. Okay. Another question. Another question?
Questions. If anyone has any questions, please type them in the Google document.
Oh, I see. I'm seeing the questions from the previous webinar.
Okay, so no, you don't want to see those. Maybe I should just pull the document up and share the screen. That was only one question that is on the document.
Oh, okay. Where will that collection point be? Well, we store those cases. Help me, Ligia, because I know we commit data sets to the GitHub archive, as I recall. Could you add something there, Ligia?
I don't think we have a well-established plan for collecting these community cases. I mean, in general, so right now the cases are housed in the Single Column Model code repository. We've already got some, quote unquote, complaints that this repository is getting heavy because of all the cases that are in there. So we have been considering splitting repositories and separating SCM code from data sets. But as far as the process for collecting the cases, so far it has been more of contact us or start an issue in the single column repository. And we have had community folks contribute cases. So that is already happening, like more ad hoc. But I think your idea is very interesting. I think it's very interesting for us, the community, to collaborate in identifying, problem cases and creating test cases and then sharing those so that we can run them together. One thing comes to mind is that we have a project called UFS Case Studies. It's not focused on single column model, but it is focused on sharing data sets for problematic cases of the UFS. So it's possible that we could expand that project to be a hub to collect this kind of single column model case as well.
Yeah, certainly we were just trying to have the cases to begin with, but it seems to me as we add more and more, and I'd like to see this greatly expand, we would need to somehow do this in a more coordinated and systematic way. So as you said in your comment, Mike B, about your summer intern trying to gather these cases, that's a really good idea. Sure, targeting issues in the GFS or any other known issues that we have with model physics. I know the Global Atmosphere Boundary Layer study in GWEX has several cases, and it would be nice to have those again in a systematic distribution method or ability to just distribute them a lot more effectively and easily, because I think some of the current distribution is a bit more one-off depending on where and how they were gathered. So it would be nice to have one-stop shopping in that regard.
Yeah, I think we would be very interested in collaborating with you and your intern on this. The use of UFS forcing to, to force the single column model, I would say is an incipient, like a budding new capability for us. So it works in the sense of, I think that, Grant Furrow has done a lot of work, and the technical aspects of that capability works. Now the science that we can do with it, I think we're just starting. So having scientists come to work with us and how we can extract the most out of this capability would be great.
Yeah, thank you.
Okay, thank you so much. So I don't believe we have any other questions. Ligia and Mike, thank you very much. Louisa, thank you so much for introducing the speakers. We're at the bottom of the hour now, so we'll wrap this up. And the next meeting will be December the 9th, because in November, the second Thursday in November is a holiday. So we will skip a month and we will resume December the 9th. Thank you all and have a wonderful rest of the day.
Stacy, can you stay on just a minute?
Yes.
And Ligia?
Sure. Thank you, everybody. Thank you,
Yeah,
Stacy.
thank you, everyone. Stacy, thank you very much. Technical difficulties.
No worries.
My wife came through with the password, but we were well into the presentation. So
Okay.
I think we did catch up, Ligia. So
Yeah. Sorry, I had to speak a bit fast on the CCPP Physics and Framework, but we did it.
yeah, I think so as
You
well.
did it. It was great.
So, Stacy, I think that the source of the technical problem was on our end, Mike and mine, not yours. But my only recommendation would be to do a test drive the day before instead of 15 minutes before.
That's what we were thinking, yes, because 15 minutes sometimes is not long enough like it was